compute the flux through the surface. Z is equal to 5 plus y squared minus x squared over the region in the plane, x squared plus y squared less than or equal to 1. Given it has upward pointing normals, and the flow that we're capturing is this vector valued function 2xi minus yj plus 2y squared k. All right, our options are, looks like multiples of pi. Pi, 2 pi, 3 pi, 4 pi, 5 pi. Did anybody have a chance to work out the answer? Or wants to take a guess? B? B as in David? Oh, B as in boy, probably. Good. B. B is the right answer. Okay, so how does this work? We're going to come back and go through the specifics in general, but we have a function that defines our surface. So this is our function f of xy. And when you're computing the flux, also they might say the flow, it's your vector valued function dot n. Well, that looks hard. So what we do is we push it down into our region. So we're not integrating on our surface, we're integrating over the region on which our surface lies. And there's a nice little formula that says if f, and I should write what f is, it's a vector valued function entries m and p. So f dot n dsa becomes minus m fx minus n fy plus p dA. And this is a useful formula to know. Well, we have our vector valued function. We have our f, so we just start putting in pieces. We have our m, f sub x is minus 2x. We have our n, f sub y is 2y. And we have our p, which is the 2y squared. Lo and behold, that becomes 4 times x squared plus y squared. You can pull the 4 out. And then you see, it's x squared plus y squared we're integrating. Our region is a circle, polar. So switch to polar. This is r squared. And when you do dA, you add an extra r dr d theta, giving you a grand total of r cubed. And with the 4r cubed, integral that is r to the 4th. Evaluate from 0 to 1. Don't forget theta, evaluate from 0 to 2 pi, which gives you 2 pi. So in some sense, it's not terrible as long as you understand the problem. And that's a big challenge. Let us not underestimate how hard it can be to understand the problem. And of course, you need to know this rule. So make sure you know how to do flows through surfaces. And good news, that's pretty much all we're talking about today. Yes?
Is p just the k value?
P is just the function, yeah, it's this 2y squared, what's in front of the k. Now you might say, well, why is this not getting any love? Here you got an f sub x, and here you got an f sub y. I don't feel the love for p. Where is it? Well, what's going on? I feel bad because I'm going to put this slide up in just a second and repeat this. Is what really happens is that this n dsa, it's minus fx minus fy1 and dA. And where this is coming from is you start with your surface z equals f of xy, and you're finding perpendicular vectors. And the way that's very easy for us to find perpendicular stuff is to use gradients. So if you take z of f of xy and move the f of xy across, you get z minus f of xy equals 0. Then when you take the gradient of this, that gives you your perpendicular vector. That's your normal vector for tangent planes. And that is what you see being stored here. So the reason that you don't see anything in front of the p is because there's just a single c and the dirt of that is 1. All right. Good. Other questions? All right. Well, we're getting near the end. A few thoughts left, but this is a nice thought. It always seems impossible until it's done. And, sometimes you might say, I'll never get it. It's impossible. But you can get it. And you will. And once you get it, it'll be like, wow, it wasn't impossible. It's done. So keep studying, keep practicing, don't give up. This is not the time of the semester to be giving up. Lean in, get it done. Okay. Well, I'm going to throw up a slide really quickly, although given the discussion we just had, we don't need it. But this is just a reminder of when we talk about flux through a surface, we're talking about flux through, in particular, I want to emphasize an oriented surface. So the surface has a top side and a bottom side. And we have a flux flowing through our surface. And we said, aha, well, if F is modeling our flow, F dot n is the rate of flow at a point, F dot n dsa is the amount of flow at that point, and then we add them up. But we never do a surface integral on a surface because that's too hard. We push down. And so we want to push down, instead of integrating over our surface, integrate over our region that the surface lies on top of. And this is the same sort of philosophy as when we think about integrating along a curve. How do you integrate along a curve? You use its parameterization. So you say, oh, I'm going to take my curve and get it down to a single one-dimensional integral function of t from my t equals a to t equals b. So we're doing the same philosophy. It's like, well, I have a surface which is up in 3D. It's all bumpy. I want to push it down, and so it's no longer bumpy. All right, and so the punchline is minus mfx minus nfy plus p. The great thing is the n and the dsa both have terrible parts, but their terribleness cancels each other out. All right, so this is a useful formula to have. Okay, now, what we want to talk about is a generalization of Green's theorem. So, let's put up Green's theorem first to remind ourselves. Green's theorem says, suppose you have a region in the plane, and we call it R. And the region possibly, well, not possibly, it has a boundary. We call it the boundary of R, so that's this notation. It's the same symbol that you see for like partial derivatives. So when you see that, that's the boundary of R. And what we want to do is we want to compare an integral over R to an integral on the boundary of R. Now we have to be careful in that there's an orientation involved. Now for curves, it's sort of like, okay, I can see I could travel two ways along the curve, so it makes sense to talk about how a curve is oriented. How is R oriented? Well, we're thinking of R as being like in the plane. So we can say, are we on the top of the plane, or are we on the bottom of the plane standing from below? So we're thinking of being on the top. So that's our orientation. And just remember the song. To the left, when you walk the curve, keep the region. We're going to sing this again, right? So we keep singing it, and then you're going to be like, okay, I got it, stop singing. All right, so the punchline is, if you want to integrate along the boundary of a function, it's the same as the integral over your region of a derivative. In this particular case, what we call the curl. And you might recall that the curl, that involves this del operator, so del cross. And in this case, it's we add an extra zero slot. In the plane, there's really just two slots. There's a m and n. But we'll add an extra zero slot, and we say this is this curl mn0 dot k dA. Now, that's not the usual way we write Green's theorem, but it is equivalent. If you work out what this turns out to be, this part down here is your n sub x minus m sub y. But there's a reason I'm writing as curl of mn0 dot k. And I should really get that dot k there, because it will help us generalize. All right, are we good with Green's theorem? So philosophy of Green's theorem, just remember, if I want to compare something on the boundary, I can look over something on the inside where I have a derivative. So there's a trade-off. The inside, the derivative makes things usually simpler. The trade-off is there's more stuff to look at. Okay, so Stokes' theorem says, why don't we put this into 3D? Like, we can think of this in 3D. So we can just add a direction, the z-axis. But of course, let's do the whole thing. So now, instead of a region in the plane, we're going to have a surface in space. And we're going to focus just on three-dimensional space. So everything is 3D here. The surface has a boundary, which we, again, use the same symbol. So what looks like the partial symbol, just boundary S. That's how we read that. So far, so good. There's an orientation. Now, the thing is, we have to be careful because we're going to talk about two orientations. The orientation of the boundary and the orientation of the surface. And they have to be compatible. So the surface, we're going to orient by its normal vectors. And so the normal vectors have two directions. So going up, I don't want to say up, it just depends on the situation. But essentially you can think about it, there's a top side and a bottom side. The normal vectors are which side is the top side. They come from the top side. The boundary, that's oriented in the same way. Namely, stand on the top of the surface. So imagine that you're a little person standing here on this surface. So I'm using these green arrows to indicate that this is the top of our surface. And now you're going to walk. And you want to walk along the curve. You're right next to the curve. And how do you walk? So that the region, in this case, when we talk about the region, I should have said your surface is to your left, to your left, to your left. When you walk the curve, keep your surface to the left. All right. So that's the setup. What's the conclusion? The integral on the boundary of the surface, f dot t, is the same as the integral over the surface, curl of f dot n dsa. Now, if you look, you'll say, whoa, these things look really, really similar. Because Green's theorem is a special case of Stokes' theorem. Green's theorem is, what if your surface is just in the xy plane? Because what happens? Well, if you're in the xy plane, what's the perpendicular to the xy plane? The z-axis. What's that vector? It's the vector k. That's the vector perpendicular to the xy plane. It's in the direction of the z-axis. So that's your normal vector. And everything else just carries over. So we've essentially done a special case of Stokes' theorem already, which is Green's theorem. So that's the idea. So essentially it's just, hey, it's Green's theorem in space. All right. Well, that's most of the lecture. We're going to go through and talk examples in a few minutes. Any questions so far? All right. Now, how do we compute things? Well, keep in mind you have two sides, and so we can compute things in two different ways. You always have a choice. And we'll again make a comment here. I'll add it right here. This is a flux of curl of f. So it's the same type of surface integrals that we just saw a few minutes before. All right. So when it comes to making this computation, we have three options. Now, what are they? Option number one, we use the left-hand side. Now, what's the left-hand side? It's a line integral. Well, what's nice about line integrals? Well, one pro, usually it's a single variable integral. That's a plus. What's a con? Well, f might be messy. So there can be a challenge when you're doing the left-hand side. But it's a perfectly valid way to approach it. Okay, what about the right-hand side? You have this side. Curl of f dot n dsa. Well, what are you doing on that side? It's a surface integral. Is there any advantage to this? It involves the curl of f. Why might that be an advantage?
We know how to solve it.
Well, we know how to solve it, but what happens when you take derivatives?
Things get simpler.
Things get simpler, right. So curl of f is usually simpler. It's something nicer to work with. We like things which are simple. And so we have an easier thing to integrate. Well, what's our con? Well, it's a surface integral. That's harder. And some of the surfaces, oh my goodness. Wow. Ugh. Ugh. Now that's not a technical math term, but that sort of captures the feeling for some surfaces that we see. Okay, now there's a third option, which is use the right-hand side plus BYOS. What is BYOS? Bring your own surface. Oh, people have watched the videos. That's nice. Bring your own surface. Now, I will tell you that when it comes to Stokes theorems, we almost always like the third option. Now, not everything will fall into this category, but we have to explain what is bring your own surface. Okay, so let's go through sort of a thought experiment. So you can imagine that you have the following, where here we have a curve, and then it's going to come down. So our surface here, S, is there. There's a big hole in the middle of it. And boundary of S is up here. All right. Now, let's orient. Suppose we orient in this way. Which side is the top side for S? Now, I know that sounds a little bit ambiguous, so let me be more explicit. If I were to draw my normal vector at this point, which way should I be pointing? Because they can't both be it. So what's the right orientation? Just pop quiz. So what do? You imagine that you're going to stand on the surface. So I have two options. I could stand sort of, if you will, over here, or I could stand over there. And I'm going to walk along the surface. Which way, which person, let's call this one the right person and this one the left person, which one, when they follow the curve, standing next to it, will have their surface to the left? Can you visualize? So, right or left? It is this person on the right. And you're probably like, but Steve, the song says the left. Well, no. The song says, keep the surface to your left. And so as this person walks along, and this requires one of those things called visualizing. But as this person walks along, they're going to be moving in this direction, and then the surface will be on their left-hand side. So it's compatible. So that says our normal vectors are pointing this way in some sense. Now, of course, it's going to this inherits it all throughout. So you got normal vectors in here, normal vectors over there, normal vectors everywhere. But okay, so there's an orientation. Now, would you want to work on this surface? No, that looks like a terrible surface. But here's the thing. It says, hey, if I want to compute this curl, it's the same as the boundary. So we say, well, let's just look at just the boundary. So here we have boundary of S, where we've just said we can pull the surface away, we can forget where the surface came from. But now we can put a surface in. Any surface with the same boundary will have this same integral. As long as the boundaries match, the integrals match. So can you think of a surface that we might be able to put here? We can put a flat disk, or if you like a circle, as some people were saying. So we can say, hey, instead of having this complicated surface S, we can have a very simple surface U. And now, what's the punchline? Well, we would have here that the integral of curl of F dot n dSA over U is the same as this integral over S. But notice, this is a much simpler surface. Okay, now, question. Which side is the top side? Going up or going down? Down. Going down. You're going down. So you got to make sure you got your orientation is one of the challenging things here. So it's probably worth 2 points when he talks about Stokes Theorem problems. And one of the things that I often like to do, now this is a harder one to visualize, is this sort of imagine, if you will, so we'll start here. Not something quite this complicated, but imagine we had like a sphere. So then what we can do is we can think about slowly deforming it. And so we're just going to push our sphere flat. And as we push our spheres flat, our normal vectors move along for the ride. So we're just pushing up into the flat sphere. So we can deform the surface. So as an example, I have a little funnel here, which looks suspiciously like a cone. But what I can do is I can just push it flat. So now, instead of having to deal with a cone, integrating over a cone, because they have the same surface boundary, the same circle, I can work over the flat disk. So that's an example. All right. So, those are our 3 approaches. Let's try it out. Let G be the surface z equals x squared plus y squared with z less than or equal to 1. Let's talk about this surface. What is the surface looking like? Z equals x squared plus y squared is what? It's a paraboloid. So a bowl shape. It looks like a parabola that you've spun around the axis. And so here's z equals 1. So we're not taking the whole paraboloid, just up to z equals 1. All right, so here is our surface G. And we're asked find the integral along the boundary of G, so along the rim of the bowl, of y minus x yz dot t ds, where boundary of G is oriented so that it is counterclockwise when viewed from above. All right. Well, so if this is x, this is y, this is z. So viewed from above says you're up here on the top of the z-axis, you're looking down. So you want it to be counterclockwise from above. So it's that direction. So that's counterclockwise from above. Is that visible enough? I think it is. Okay, so we're going to compute this. And we'll do it in 3 ways. And hopefully we get the same answer all 3 times. Okay, so let's just straightforward compute it. What do we have here? It's a line integral. So we can write this. So this is the left-hand side, if you will. So this integral, another way to write this, if you see a dot TDS, it's the same as the first function dx plus the second function dy plus the third function dz. So this is another way to write the integral. So the dot TDS is the dx, dy, dz. Okay, so let's take a look for a second. And what does boundary of G look like? So G is the bowl. Boundary of G is what? It's a circle. Can you tell me anything more about the circle? Radius 1, very good. Now it's a circle in 3-dimensional space. Where does it sit in the z direction? Z equals 1. So boundary of G, we have a parameterization. So we can say, all right, so the boundary of G is parameterized by something, something, 1. How do you parameterize the unit circle without going crazy? Sines and cosines, very good. And counterclockwise too, I might add. Okay, so if you're going to parameterize the unit circle counterclockwise, what's the x, what's the y? Cosine and sine. So that's cosine and sine are built-in natural parameterizations for the unit circle in a counterclockwise direction. Okay, so we say, cool, we know how to compute line integrals. What we'll do is everywhere we see a y, what will we put? Sine t. Everywhere we see x, we put cosine t. Everywhere we see z, we put 1. dx becomes the derivative of cosine, which is negative sine. dy becomes cosine. dz becomes 0. And there's one other thing we forgot to write for our parameterization. Where does t go between? For a full circle, 0 to 2 pi. Okay, so we rewrite this as an integral just in t, 0 to 2 pi. And be patient as we carefully work this through. Sine t times the derivative of cosine t, which is negative sine t. Whoops, negative sine t. Derivative of cosine. Minus cosine t. Derivative of sine t is cosine t. And then plus sine t times 1 times 0 dt. All right. Cool. Now what? Well, does anything simplify? It's negative 1. So this becomes the integral 0 to 2 pi of negative 1, which is negative 2 pi. Okay, so that's doing it as a line integral. We still have plenty of space, but we still have other things to compute. All right, what's next? The right-hand side. Okay, so the right-hand side says, hey, you know what? This is, by Stokes, this becomes the integral over our surface of G of the curl. Well, we better compute the curl. So we're going to do that really quickly. The curl of y minus x, y, z. How do you compute curl? It's a cross product. It's your del cross f. So you have your ijk, your partial x, partial y, partial z, and then you put in your entries. So our entries are y minus x, yz. Okay, so we get partial y of yz, z. And that's in the I direction. Partial z of y, 0. That's in the j direction. Partial x of minus x, -1. And that's in the k direction. Go the other direction. Partial y of y is y. And that's in the k direction, but we subtract because we're going in the other direction, right? We're going up instead of down. Partial z of minus x, 0, and that's in the I direction. We'll subtract that. And partial x of yz, 0, and that's in the j direction. So this becomes z0 minus 2. Okay, so we know this is z0 minus 2 dot n dsa. All right, so we say, hey, this is a flux through a surface. So, according to our handy formula, a flux through a surface is the integral over our region. We'll talk about that region in just a second. We have our minus mfx minus nfy plus p dA. That's our generic formula for flux through a surface. So we need to fill in some pieces here. First off, what's our function f? Our f is this x squared plus y squared. F of xy. Okay, so term by term, we have, this is going to be minus our m, which is z, times f sub x, which is 2x, minus our n, which is 0, times f sub y, which is 2y, plus our p, which is -2. And all of this is dA. All right, well, what's our region? Well, the question is, when we do a surface integral, we go to a region. What is the region? It's, if you were to look down the z-axis, what would you see as the sort of the shadow of your surface? It'd be the unit circle in the plane. So now what we have to do is we have to integrate. And there's one other thing we have to worry about is we have to replace this z, because we can't have any x's or y's. So what would it get replaced by? Yeah, you use your z as your surface definition to replace anything that's left. So, whoops, I switched colors accidentally. Okay, so this is equal to the integral over our region of minus 2x times x squared plus y squared minus 2 dA. Now, we could spend a few minutes and work it out, or we could say, aha, ha ha ha, ha. Okay, I don't know which way you want to do it. All right, that's our few minutes working it out. The question is, do you want to do all that, or do you want to be like, aha, ho 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 ho, ha? Let's split this into two parts. Integral of 2 over our region, minus 2 over our region, x times x squared plus y squared, dA, minus 2 integral over our region, dA. One of these integrals is easy, the other integral is easy. Which one is which? Which one is this one? It's easy because we're integrating 1 dA. So when you integrate 1 dA, what do you find? Area. How much area is there in a unit circle? Pi. So this is pi. Now this one you're probably like, Steve, you lied. You said it was going to be easy. It doesn't look easy to me. It looks rather odd. Peculiar. Strange. What can we say about this integral and why? It's odd, which means what? So why do you say it's odd, other than the fact that I said it? What makes it odd? If you look over your region, you say, hey, let me look at the contribution of this little piece versus this little piece over here. How do they compare? They're the same in magnitude, but opposite in sign. So that these two pieces will cancel out. But you can always pair up pieces across so you get cancellation. So you get 0 by symmetry. So this is 0 because of oddness. So what do we get out as our final answer? Negative 2 pi. Okay, so that is the right-hand side. Right now, the right-hand side is not looking too good for me because you're probably like, I preferred the left-hand side. But we've got a third option. Option number 3. Bring your own surface. Okay, so we bring our own surface. Here's a boundary. We just have to fill in our surface. What's a good surface there? Yeah, a flat circle, a disk. Now, what's the orientation for this? What's our normal vector? Are we going up or down? Up. So what is n? 0, 0, 1. Our normal vector is 0, 0, 1. So when we talk about n, it's a unit normal vector. Okay, so we say, aha, we can say we're going to work over h. So we're going to do our option 3, right-hand side plus BYOS. We say, hey, this is the integral over h of, the curl's the same. We can actually save our work with curl later on, dot 0, 0, 1. What happens when you take this dot product? You get negative 2. So negative 2 is a constant. You can pull it out. It's negative 2 integral over your surface, DSA. What is it you're finding when you integrate negative 2 over your surface? It's the area of your surface. And our surface, it's a unit circle. And so that means it has area pi. So we get negative 2 pi. Nice. They all matched. Coincidence? No. That's what the theory says. And now that we've done one problem, we have enough time left to maybe talk about one more. That's okay. We'll get time to do this again next week.
How are you just able to look at the integral of x times x squared plus y squared and know that?
Because I'm an odd person. And odd recognizes odd. You know, it's like game recognizes game. Odd recognizes odd. Right? All right. So we should do one more. One more. Let's see. Okay. Here we go. Speed run. So this was from an old exam. Let G be the surface. 1 plus z squared equals x squared plus y squared. Z going from negative 1 to 2. Does anybody recognize this surface? Ooh, sphere sounds like it would be cool, but it's not a sphere. Oh, saddle would be cool, but it's not a saddle either. Oh, it's not a cone. Don't worry, you're running out of solids. Not a paraboloid. Hyperboloid. How many sheets? 1 or 2? It's a 1-sheet hyperboloid. Very good. Okay, so you have z equals 2. Z equals -1. Here's your surface. So we have our surface G. And our orientation has been given to us. Our normals point away from the z-axis, so they're pointing outward. So here's the orientation for our surface. Find the integral on the boundary of G, and notice the boundary of G has how many pieces? 2 pieces. It's like it's a holy boundary, just like in Green's theorem. You could have boundary with multiple parts, so you're perfectly allowed to have more than 1 piece. Cool, 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 cool. So find the integral on the boundary of G, these 2 parts of this thing dot TDS. Now, this does not look pleasant. That is not cosine squared x, that's cosine x squared. That's not sine squared of y, that's sine y squared. We do not want to touch that. So that's a signal. When you see messiness, it's like we don't want to do that. So we want to apply the theory. So let's bring our surface, bring our own surface. Instead of the hyperboloid, what can we use? We can use a pair of circles. Now, let's treat these individually. The top circle. Should our normals be pointing up or down? Down. You can imagine that you push it up in here, right? And just bring your normal vectors along for the ride. So it's just you're pushing it up in. Downstairs, so are we putting up or down? Up. So at the top we have 0, 0, -1. Downstairs we have 0, 0, +1 for our normals. So we're going to do these 2 pieces here. It sounds like it'll take a while, but don't worry. It won't take that long. We are going to call this here F. We know that this is equal to the integral over our new surface. We'll call it H. H has both circles of curl of F dot n. Now, we need to find the curl, but do we care about all the entries in the curl? Which entry do we care about and why? The last entry. Why do we say we don't care about the first 2 entries, as I point to the reason? Because you see zeros here. It's hard to recover from times 0. Okay, so we take the curl of this terrible expression. So curl of y z 3x plus z squared minus y cubed cosine x squared plus sine y squared. And all right. I, j, k, partial x, partial y, partial z. And y, z, 3x plus z squared minus y cubed, and I don't care. Okay, I don't care. I don't care. This is the I don't care symbol. All right, for k, we have k partial x of 3x plus z squared minus y cubed, 3. And we also have partial y of yz, z, and then we subtract that. Okay, so we say, it's 3 minus z. So this becomes integral over the top circle of something 3 minus z dot 0, 0, minus 1 dsa plus the integral over the bottom, again something 3 minus z dot 0, 0, plus 1. Now, the top. What can we say is true about z on the top circle? Z equals 2. So 3 minus 2, 1. This dot that all together gives us -1 area of the top Now, on the bottom, z equals minus 1. 3 minus minus 1? 4. So this could be 0, 0, 4. So plus 4 area of the bottom. Well, how much area is on the top? That's right, it's 5 pi. Good. How much area is on the bottom? 2 pi. Excellent. 4 times 2 pi, eh? And so our answer is 3 pi. Now you're probably wondering, wait, where did 5 pi come from? So upstairs, z equals 2. X squared plus y squared equals 5. So your radius is square root of 5. So the area is pi r squared, pi times 5. Downstairs, x squared plus y squared equals 2. So your radius is root 2. So you get 3 pi. So yes, I skipped some steps, but that's the idea.